You have audio? I can't quite hear. Yeah, there you go. Okay, great. So I'm going to talk about generative AI, but a little different than what you probably have heard of. Generative AI for decision making. And we'll start with who I am. And let's just get this show on the road. There you go. So I'm AVP at Cognizant, AI Labs. I run a small research team there in San Francisco. But the fun fact about me is that I'm actually a professor, computer science at University of Texas at Austin. That's my day job. And for a long time, I played the game of publish or perish, or produce PhD students or perish. But after a while, it seemed like I'd like to take this research to the real world and change the world with the technology that we've been building for 30 years. And it's been great fun. It turns out that the world does not want to change, but you have to work at it really hard, and eventually you'll probably make some headway. And we've been working on it for quite a while, and I'm going to tell you about some of the results we have and some of the opportunities that we found. So indeed, generative AI, you already know a lot about large language models and probably also the vision image generation models. But there's a third leg on the stool, and that is on decision making. And that means that we are generating designs, perhaps solutions that don't exist before, and there's no data on them. They are generated on the spot using different techniques than, say, image generation and language generation. So the challenge here is something like this. For instance, the picture here in the middle, the train, that's actually Shinkansen in Japan. And they had a challenge in version 2.0. They wanted to create a nose cone that would be as sleek and aerodynamically effective as possible, but also wouldn't generate a bang when it went into a tunnel, like the earlier designs did. And the engineers were having a really hard time doing that. So they invoked this kind of generative AI design system, evolutionary optimization, and came up with that design that you see here on the image. It looks a little funny. It looks like something that people wouldn't necessarily come up with. But if you have generative AI system that can crank a lot of designs, test them, evaluate them, and take advantage of large-scale compute, you can come up with that. There are a couple of other examples here. Designing a neural network that's very complex, perhaps for controlling robots. And on top, there's an example case that we built on recommending non-pharmaceutical interventions for the COVID-19 pandemic, like whether you should close the schools, when you should do it, limit transportation, and so on. All of those are decision-making problems, design problems, and they require coming up with a strategy that you apply multiple times over time. And this is a little different than, say, image generation and language generation is. And it's also remarkably ready. We can already do this, and we've been doing this for decades already. But now, with large language models, we can actually leverage it, take it to the real world, have an interface that people can work with, and actually build these applications a lot easier. That's the idea. So why would we want to optimize decision making? Why now? Well, organizations have today a lot of data. All the different retail stores, educational institutions, scientific institutions, healthcare institutions, they create huge amounts of data all the time. And there are some very good predictive models that allows them to predict what will happen in some future case that comes through the door. But what's not yet there is recommendations. What do you do about it? If you get a prediction, what should you do? How should you organize your curriculum, or what kind of treatment should you recommend? That's still a different decision problem. I mean, it's not predicting what will happen, but like what will happen, but it's what you should do about it. And that's a different beast. We need to come up with a new technology to come up with those prescriptions, and we also need to do it in the real world without hurting the world. You can't experiment on real patients, for instance. We have to use AI to simulate those patients. So the first technology is evolutionary AI. I already mentioned that in the context of designing the new nose cone for the Shinkansen. Technically, what it is population-based search. So you have multiple individuals in your population that you are trying out. Like here is a very difficult landscape. You try to find a peak. So you have a population of hundreds of different solutions, and you evaluate how well each one of them does. And then you use evolutionary operators like crossover and mutation to create new solutions, imitating biological evolution that way, computationally. And these individuals are not just individual search points because they talk, in a sense. You do crossover. You take pieces of one good solution and combine it with another one, and you get something even better. You know, the children are better than their parents. That's what we're hoping for. And over time, then you find some really good solutions that are on those peaks. And it doesn't matter that the landscape might look like that. We don't have to climb the nearest hill like you would do in reinforcement learning or gradient descent. Evolution actually does not really care about those hills and valleys. It will find multiple peaks very easily because there's a population. So it's geared towards massive exploration and massively large spaces. So for instance, there's some work on multiplexer design. If you generate it as a search problem or define it as a search problem, for 70 bits, a multiplexer search space is 2 to the 2 to the 70th. Now, that sounds very compact, but if you write it out as a decimal number in 10-point font, it will take light 95 years to go from the beginning to the end of that number. That's how many states there are in that search space where you have to find the optimum or correct solutions. And evolution can do it because it has this population. Some of those individuals have some of its multiplexer behavior, right? And then you recombine them with others who have some other parts. And this way you can make progress even in space that's large. And similarly, if you have a very high dimensional space, like maybe hundreds or thousands, even millions of dimensions, knobs that you have to turn at the same time to define the optimum state, you can still do it. Typically, humans can handle about 7 plus minus 2. Bayesian optimization, maybe 10, maybe 15. There's work by Colin Moydeb and others that show that you can optimize 1 billion parameters at once. So there's tremendous opportunity to scale up, and that, of course, means that there are many problems in the real world that we can actually address when we otherwise couldn't. So that was the first technology, evolutionary optimization, and that's the core technology, just like transformers are for language models and diffusion networks are for vision, image generation. So evolutionary optimization is there for decision making. But we need another component. We need a surrogate for the real world. Like I said, you can't really experiment treatment options on real patients. You have to have a digital twin for the patient. And then you can try how well your suggested solutions might work. So this is the approach. You have a predictive model, that vertical model, that's looking at the context and actions, and then the outcome that resulted. You took this treatment for this patient, and this is how well it worked out. You can train that with historical data. That's the data that organizations have. And you can build such predictive models pretty easily now using neural networks or random forests or whatever you like. Now, once you have that predictive model, it can act as a digital twin. And now you can search for those decision strategies. And they might be as simple as a neural network that maps the context directly to actions. And then, once you have that neural network, you try it out on a number of cases and ask the predictor, how well would this decision maker perform in future cases? And that's what the surrogate optimization is about. That you don't test these solutions in the real world, you test them in simulation or in digital twin first. Once you have a really good solution, then you might take it to the real world. Okay, so that's actually the approach that we've developed at Cognizant AI Labs over the years, several years now. And now we have actual platform, a product, an interface that allows you to work with it. So it orchestrates all these elements for decision making, predictors, prescriptors, uncertainty, explainability, interactivity, into a common platform. And this way you can then optimize whatever your problem is, taking the historical data to train the models and then apply them to the real world to optimize your KPIs. So at this point, I'm actually going to look at just the architecture, and then I'm going to give you a live demo. Hopefully it will work. We'll see. So this is how we orchestrate those pieces. On the bottom there are elements that you drag and drop into the model, into the system that you build under AI. And it includes several LLMs, large language models. Those that work with data, those that work with our solutions, explaining them. And in the middle there, you have those other elements, predictive AI, uncertainty metrics, as well as prescriptive AI. So they work together in order to put together this system that allows you to design decision-making systems. So let's go to the demo now. It's been patiently waiting here in the background. And this is actually live connection to the internet where we are serving this system, Neuro AI. Yeah, it seems to be working. So there are a bunch of these projects that we have as demos in various areas: finance, engineering, healthcare, media. But I'm going to do the call center because that's easy to relate to for multiple industries. So you have customer service call center. Customers call in, they have a problem, and you have to listen to them and then react and give them incentives, make sure that they don't leave. And then you get rewarded if you actually solve this problem well. So we collected ahead of time a bunch of data on these call center interactions. And this is something that happens every day, and very soon you have hundreds of thousands, maybe millions of these interactions coded. And that becomes the training data for your surrogate. And the surrogate becomes basis for optimizing the decision making. So here are some of those variables. What is the membership status of the caller? There might be values like existing or lapsed or new. There might be variables describing how long the call took, for instance, whether it was long, medium, short. And some of those somewhat a little more difficult ones, like what is the tone of voice? Was it angry or anxious or neutral or sad or something like that? All of these are variables that describe what the caller, or what the quality of the call, or what happened at the call. So those describe the context. And then we have a bunch of variables here with a different color that describe the actions, what you can do as a result in this call. So you might respond with action like being apologetic, empathetic, informative, reassuring. You could refer to others. You could give some discounts, 10%, 20%, 5%. These are all decisions that the customer service representative needs to make. And they then result in some outcome. So for each call, there's some action, and then there's an outcome. And the outcome might be the cost. If you give discounts, for instance, they cost some amount. The rating of the call, the customer eventually rates the interaction. And also the probability of retention of that customer. So those are the variables that we want to optimize. So that's what we have. We have context, we have actions, and we have outcomes. And that data set then allows us to build these models. And I've done that ahead of time. Here's the same graph as I showed before. It consists of all these elements, like the data LLM allows you to perhaps fill in some missing values. So we give it a prompt describing or asking it to describe how it would go about filling the values, and then we could ask it to fill some values in. And that sometimes helps. Values are always missing, and we can use the rest of the data to guess what they should be, and then train the models better. Here is an analytical LLM. Still looking at the data, this LLM actually might give you sensitivity analysis, or it might even find some interesting patterns in the data, insights into the data. So there we use LLMs before we even start to build these machine learning systems. And now remember, we had 3 different objectives. Here we have 3 predictors, each one predicting a different outcome. This one is the cost. This one, I think, is the survey rating. And then we have the probability of retention. So each is a different model. You can choose from alternative ways of modeling it. And you might want to, depending on what the data is like. And then we have uncertainty models. These are Gaussian process models that estimate the certainty around the prediction that we make. Now, we don't need it for the retention rate, because that's a probability itself. But the other ones, if we're predicting the cost, we want to know what's the 95% confidence interval around it. And then those predictions interact with the prescriptor, which here is, again, a system that makes recommendations. And we can choose whether we want to make it rule set or maybe a neural network. A rule set has the advantage that you can look at the rules and it can be explainable. And here's what we want to do to the objectives: minimize cost, maximize surveys, and retention. And then we have an output LLM that actuates actually whatever that comes out of the prescriptor, then the LLM can actually execute it. So it might make a recommendation to the human operator, or maybe even send a text to the customer if that's an automated system entirely. So this actuates what the prescriptor makes as a recommendation. So this takes a little while to train with the data, so I've done that ahead of time, and I trained a rule set to do it. So let's look at what those systems look like, those models look like once they have been trained. So here's actually some data that shows that indeed over time, as we are learning to prescribe better and better decisions, recommendations, our cost goes down, so we get better at optimizing that variable. And same is true to some degree also with the survey rating and the retention probability, they go up. And here is the actual set of prescriptors that we come up with. Remember, we had 3 objectives, so there are many different ways of trading them off. Some people might prefer to lower the cost, and others might emphasize retention. So these are different trade-offs. Each one of them is a valid prescriptor, but with a different trade-off. And it's kind of complicated in 3D. In 2D, it's a little easier to see. But there's another way of looking at it from the point of view of the decision maker, which is in terms of this parallel coordinates. So now the decision maker gets to choose what trade-off they like. So they might go here and say that I actually really care about, say, retention probability, and therefore choose some of these that are really good prescriptors in terms of retention. And then they go that I actually also want to have a low cost and go here and select some of these. And maybe there's then the winner, one that this particular decision maker likes the best. It's trade-off, picks that, and then we'll see how well it works. That can be then deployed. And let's go here and go to the decision-making system with that prescriptor. So now this is actually deployed. And now new cases come in. Here's one new such case. While we are waiting for the prescriptor and predictor to load, we can look at a little bit more here what the prescriptor. This is actually a really simple one. It only consists of 2 rules. And we can then use the LLM to explain that or interpret that in actual language. So now you get natural language description of what this prescriptor is looking at, how it's making its decisions. And you can also ask LLMs to give you some insights. Why is it doing that? What's good about it? What do these rules do? What are the risks? What are the biases? LLMs are really good at that, and we can bring them into this decision-making system in order to give you the decision maker more insight into what's happening. And then, so now we have the prescriptor and predictors loaded from the memory that I trained earlier. And given this new situation, now there's a new caller, and the system records all these variables and recognizes that this is an existing member that's angry, speaking fast, it's about billing, and we can ask the prescriptor, what should we do about it? And now we get the recommendation. Be apologetic, maybe give them 10% off, something additional for free and triple points and so on. And then we can ask the predictor, remember the surrogate for the world, what do we expect that will happen in terms of those outcome variables? And here we see that we have some estimate of the cost with confidence interval, and there's a high probability that we'll actually retain this customer if we do that. And you can go here and you can change what you do, and just to try it out, this is what the operator can do. Maybe give a little bit less discount, or maybe none at all. Since we have a high probability, we could try something that's a little simpler and predict again and see whether we get a better solution. Oh yeah, now we have a low retention probability. Some of those incentives were really important. And this way the decision maker can explore the different alternatives and convince themselves that this is actually a good solution. And that's important. If you are deploying AI into the real world, you still want to have humans in control. And in this way, you can interact with the system, bring in your own creativity, explore those possibilities, and find out indeed that this is the best possible thing you could do. Oh yeah, and there's one more thing that you can do. There's an LLM here where you can ask questions. Like I could ask, for instance, how can we increase? Let's do that. I'll have to put this down. One second. Okay, so I asked how can we increase retention probability because it was kind of low, and it should come up with something. Yeah, there you go. So it gives you some insights into the data and makes some suggestions of what you could do. And this is based on intelligent prompting and letting the LLM know how the system works, what the variables are, and so on. So you can use these and then go back and edit. So that's basically the demo. And let me go back and show there's a bunch of these different projects we could look at, but because in the interest of time, I want to leave some time for questions. Let's go back and just conclude. So yeah, AI has become generative, but that doesn't mean just LLMs. It means that, or vision, that we can also generate decision-making strategies using a little bit different technology. And the Neuro AI is an instantiation of that. It orchestrates this Gen AI, large language models, and predictive and prescriptive and uncertainty models and explainability models so that you can deploy them in the world today. And you get creative solutions beyond what humans could do. And also something that you can understand and trust. And part of it is things like interaction and LLMs that explain where those decisions come from. And in this case, and in this way, we can deploy them in the world. So we have, I think, 8 minutes for questions. Thank you.
Does anyone have a question? I will bring you the mic. Oh, here we go.
Hi, my name is Dawn. I'm with Pace Industries. I saw the pre-setup setups you guys have, like for the health calls and stuff. Is there any way to customize a scenario to train our AI?
Yeah, of course. I mean, all of this is based on your data set. So we started with a window into the data here. This is a data set. So we can bring in your own data set here, your own customized variables and values, and then build it for you. Now, there's also a way of utilizing publicly available data sets. If you have very little data, we can use public data sets to give it crutches, give it some basic functionality, and then customize it to your own on top of that. Yeah.
Anyone else? Last chance.
Hi, John, Sam's Club. I was wondering if you could maybe speculate about what kinds of problems this sort of decision-making AI might be able to address in the future.
Yes, it's supposed to be very general. I mean, if you look at these demos that we already built, they span a lot of areas. There's gas turbine optimization. I mean, this is a engineering design problem. There's diabetes medication to minimize hospital time. This lending club is deciding whether to give a loan and what kind of interest rates and what's the chance of defaulting, for instance, optimizing those variables. This is network customization, price optimization. A common one is marketing, like deciding how to allocate your marketing dollars to different channels. So it's pretty agnostic with respect to the domain, But what you do need is data. You do need something where you have the context and actions and outcomes. Now, a lot of companies have the context and they know what the outcomes are and can you measure it. But sometimes the actions are not recorded because there are humans making these decisions. There may not be a record of what they actually did. That's what we found. But as soon as you recognize that, you can start recording those, and in a year or so, you do have already data that you could use to build a system. Now, so that's one part of it, like what's feasible. But also, when would you want to? I mean, you would want to have a problem that's complex enough. And that means that there are enough variables that you can't just do it in your head. Like I said, humans can do 7 plus minus 2, but what if you have 100? And also variables that interact in nonlinear ways. So sometimes you give the 10% incentive, but that only works if the person is, say, already been a customer for a while. So there's like nonlinear interaction between two variables. Those are hard for people to understand, but you can learn them from the data and then utilize them in making the predictions. And that's why you would want to bring in a system like that, so it automatically discovers something that you don't already know.
Any more questions? Oh.
Hi, Cannon Porter. There at the end, you had several variables, several levers that someone could pull to explore, optimize what the outcome would be, et cetera. Is there any way to show which variables are most important, or are there interaction terms between?
Yeah, absolutely. And that starts already in the design and orchestration here. So we can look at just the data, and that's the typical data analysis. So here the LLMs, oh, this was the wrong one. This was the one that actually looked at filling the data, but the analytics LLM can be utilized in that role. So it can be doing sensitivity analysis. And then perhaps also find those patterns. So that's one way, but that's also something that people are already doing. Now, but when you actually build the prescriptor, this element here, then you can look at the rules. Let's see, that was a little bit further down, we have to go. The interpretation and insights in the rules. So now, if we pick a prescriptor, we can look at what the rules are in it. We'll just go to this graph and pick something. And now we see the rules, and we can get the insights. And part of that is that we'll actually understand precisely answers to that kind of questions. Why are these rules here? What's most important? And that is actually a big part of also being deployable, that people want to understand what they are deploying.
Okay, last question.
Trying to think the best way to ask this question. So let's say you have your ERP data, your WMS, your TMS. Could you bring in not private, but data from like a Sam's Club or for a Target? Like if you're a supplier, take that information, use it in your data stack, and be able to push out like where we should push certain goods or where lanes might be able to where we might need more trucks, right? And it just be generative decision making, like that just happen automatically?
Yeah, that's a very good question. I'm expanding it a bit. So we need to build the predictive model based on existing data. So whatever has happened in the past, we capture and we learn about it. Now, what happens if there's an opportunity that's actually not being explored? Because sometimes you just apply the same strategy over and over again, and your data does not have enough diversity. And that is actually a very fundamental question, and there are techniques developed in order to extrapolate, go beyond the past experience. It's still machine learning based, but there are techniques that have to be added on machine learning. For instance, you model the context separately. That's one way of doing it, and then when you have a separate context model, that allows you to extrapolate a little further. You may also have to be putting on constraints of what is actually feasible. Can you send a truck to Alaska or something? I don't know. So to keep it reasonable. But there are mechanisms for allowing you to extrapolate beyond what's already in the data, but they are limited too. So we need to know ahead of time what are the reasonable limits, and then if there's no data at all, maybe it's time to try to collect that and actually get some more data, just in perhaps a simulation or maybe in the real world where it's actually cost effective. It depends on the application where it can be done. But that's one of the most important questions to ask when you actually build the data set. Not just that if there's enough data and if it's nonlinear, it's hard enough. Is there enough diversity in the data that allows you to discover things that you don't already know? I forgot to say that as an answer to your question, but that's another dimension that we need to look at when we look at whether this is a good application.
Thank you, Risto.
Yeah, thank you.